So good morning, everyone, and thank you for joining us. And thank you, Chiara, for this introduction. I'm delighted to participate in the climate coffees and to share with you some results from our recent publication, which explore how we can use Copula-based approach models to better understand the joint dynamics between sea surface temperature and chlorophyll-a concentration in the Strait of Gibraltar, comparing satellite observation and hindcast models. So this work is a collaboration between University Ad Malik Saadi, Durham University, and Mohammed VI Polytechnic University in Bangalore. So the objective of the study is to understand the role of small pelagic fish in the marine food chain and how their abundance is influenced by two key variables, the sea surface temperature and the chlorophyll-a concentration. So to model this dependent structure, we use a parametric Copula-based approach comparing both satellite observation and climate model outputs. The following diagram illustrates the marine food chain, highlighting the position of small pelagic fish in this chain. These fish act as intermediaries, consuming phytoplankton and serving as prey for larger predators. And any changes in SST and chlorophyll-a concentration can lead to the migration of the small pelagic fish and affecting then the entire marine ecosystems. In this study, we use chlorophyll-a concentration as an indicator of phytoplankton abundance, making it a crucial variable for understanding marine productivity. This flowchart summarizes our methodological approach. Our aim is to explore the nonlinear dependency between SST and chlorophyll-a concentration and to evaluate how well climate models can capture this relationship. We use MODISA satellite and hindcast simulation from semi-6 models. And to correct biases in the model outputs, we apply the multivariate bias correction algorithm. The steps include, first of all, identify the best fit marginal distribution using the cumulative distribution functions, the goodness of fit test, and AIC and BIC information criterion. Then modeling the joint behavior via parametric copulas, and finally comparing satellite and model-based dependency structure. Our study area is the Strait of Gibraltar, using data from our MODISA satellite, which is the moderate resolution imaging radiometer. We study two variables, the sea surface temperature and the chlorophyll-a concentration, with a spatial resolution of 4.64 kilometers and a monthly temporal resolution. The period spanned from August 2002 to September 2022. This scatter plot may show some clusters may indicate stronger relationship in specific periods, like here, while outliers more correspond to extreme events. And the second figure shows spatial correlation. Blue areas indicate strong positive correlation, while areas in blue, in the red color, indicate strong negative correlation. However, correlation analysis alone fails to capture source dependencies or nonlinear effects, which is why we use Copula-based modeling. So to simplify the principle of copulas, we consider two random variables, x and y. In our case, x represents the sea surface temperature and y the chlorophyll-a concentration. The univariate marginal distributions denoted by fx and fy are the cumulative distribution functions of x and y. They describe the behavior of each variable independently. The joint distribution denoted by h captures the combined behavior of the two variables. It tells us how the probability of one variable is related to the probability of the other. And finally, Scalar's theorem is the fundamental theorem of copulas that link the joint distribution h to the marginal distribution fx and fy via a copula functions. There exist several families of copulas. First, the elliptical family, like the normal and student T copula, and the Archimedean family, which includes Frank, Gamble, and Clayton copulas, and others. And in our study, we identified the Clayton copula and and the town copula. This town copula, which is an extension of the Gamble copula with the asymmetric picant function. So to identify the best fit marginal distribution, we tested 5 marginal distribution, the normal, log normal, gamma, Weibull, and Gamble to fit each marginal. And we selected the best fit based on the cumulative distribution functions, the goodness of fit test, and the AIC and BIC information criteria. We start by identifying the marginal distribution for each variable and for both seasons, the MIM, March, April, May, and SON, September, October, November. Here we compare in these figures the theoretical and empirical cumulative distribution functions for SST and chlorophyll-a concentration during the MIM season. So as shown, the empirical and theoretical distributions are quite close, making it difficult to make a definitive choice based on CDFs alone. And here we have the result for the SON season. So comparing the theoretical and empirical cumulative distribution functions continues to show similar challenges. To refine our selection, we use goodness of fit tests, such as Kolmogorov-Smirnov, Kramer-Vomises, and Anderson-Dellin. The statistics, as well as the AIC and BIC information criterion, guide us in determining the most appropriate marginal distribution. These tables show the result for the MIM season. So considering the minimum values, Gamble's law was found to be the best fit for both SST and chlorophyll-a concentration. However, for the SON season, the normal distribution was identified as the most suitable for SST, while the Gamble distribution remained the best for chlorophyll-a concentration. So after selecting the best marginal distribution, we moved to copula selection. This table shows the fitted copula model using the minimum AIC. For the MIM season, the best fit was the rotated town copula type 1, rotated by 270 degrees. And for the SON season, the rotated town copula type 2, rotated by 270 degrees, was selected. And here is the equation of the town copula and the picant functions denoted by A, where theta is the parameter of dependence and delta 1 and delta 2 are the asymmetry parameters. When delta 1 is equal to 1, we obtain the town copula type 2. And when delta 2 is equal to 1, we obtain the town copula type 1. And if delta 1 is equal to delta 2 is equal to 1, here this reduces to the Gamble copula. And here we have the equation of the rotated copula by 270 degrees. Here we have the CDF cumulative distribution functions and their contours, and the probability density function and their contours for the MIM season in this site and for the SON season. So in the MIM season, the town copula type 1 had parameters theta equal to minus 2.11 and delta is equal to 0.35 and the Kindle-2 is equal to minus 0.24, indicating a low negative toll dependence. On the other hand, in the SON season, the town copula type 2 had parameters theta equal to minus 2.36 and delta equal to 0.27 and the Kindle-2 is equal to minus 0.21, confirming even the weaker dependency. So in both seasons, the dependency between SST and chlorophyll-a concentration is weak and negative is weak. This is due to the high circulation in the Strait of Gibraltar. So moving on to the second part, here we use 6 semi-6 hindcast models to access climate variability. So monthly SST and chlorophyll-a concentration were extracted at 100 resolution. The MBCP algorithm uses a two-step approach to correct biases in climate data. First, univariate quantile mapping is applied to adjust each variable by matching its statistical distribution for the observed data. Next, multivariate rescaling is performed using Kolesky decomposition to preserve correlation between variables and achieve realistic dependencies. The process iteratively refines the corrections until the K-matrix converge. This hybrid method provides bias-corrected historical and projected data while maintaining accurate marginal distribution and multivariate relationship. So in this study, we are interested in the historical part. However, this corrected projection will be an important starting point for future research. This will involve looking into the impact of climate change and exploring future scenarios related to these variables. Here, a Taylor diagram illustrates the performance of different climate models in reproducing the historical SST variability. The models are compared to observation in terms of correlation here, the standard deviation, and this black arc represents the standard deviation of the observed data, and in terms of centered root mean square error, which is represented by this blue arcs. The dots represent the models before bias correction and the stars after bias correction. So we can see that the CMCC model, this one represented in the blue color, represent a height correlation. We have here 0.8 in the correlation and an error approximately 0.55 degrees Celsius. And in the S1 season, the model represents a correlation of 0.9 and an error of approximately 0.6 degrees Celsius. So we selected the CMCC SM2 model for the SST models. So unlike SST, chlorophyll-a is more sensitive to model uncertainty. As can be seen here, the correlation values are generally lower and in some cases negative, like here. And the error reaches 1 milligram per cubic meters in the case of the NOR-SM2 model, which is very high. Therefore, we selected the EPSL model for the MIM season and the CSM2 model, the green one here, for the S1 season, as this model showed the lowest error. These figures show a comparison of the CDFs and of the SST between the CMCC model and the MODISA observations. As can be seen, the model align well during the MIM season. However, some discrepancies appear in the center during the S1 season. So overall, the selected models provide a reasonably accurate representation of historical SST behavior, which support their use in further analysis. Here, there is a notable overlap between the historical MODISA satellite data and the model outputs. And despite this favorable correspondence observed between the corrected and historical CDFs, the Taylor diagrams reveal the presence of residual error. It is therefore necessary to conduct a more detailed analysis examining the dependency structure between the variables in question. So we apply the same goodness of fit procedures as in the first part of the study, testing various candidate distributions, and these tables show the results for the MIM season. Here we found that the normal distribution is the most appropriate for the SST model, while the Gamble law is still the best fit for the chlorophyll-a model. Meanwhile, for the S1 season, the Weibull distribution is the most appropriate for the SST model, while the Gamble law is again the best fit for the chlorophyll-a model. This table summarizes the Copula family selection based on the minimum AIC. For the MIM season, a rotated 90 degrees Clayton copula is selected, while for the S1 season, a rotated 180 degrees Town copula type 2 is selected. And here we have the equation of the Clayton copula and the rotated copula by 90 degrees and the rotated copula by 180 degrees. So here again, we have the CDFs and the PDF and their contours. So for the MIM season, the rotated Clayton copula had parameter theta equal to -1.31 and the Kindes is equal to -0.39, which reflect a strong lower tour dependence. For the S1 season, the rotated town copula type 2 had parameters theta equal to 2.88 and the delta is equal to 0.38 and the Kindes is equal to 0.3, which capture positive dependency in the upper tour and also the asymmetric behavior. So, in conclusion, the key findings are we found the gamma distribution which show a good fit for chlorophyll-a in both satellite and model data, reflecting its sensitivity to extreme events. The SST marginal varied significantly across model and season. We found the log normal, Weibull, and Gamble distributions. The MBCP algorithm was applied to correct climate model biases before copula fighting. For MODISA data for the selected copulas, we selected the town copula type 1 and 2, which capture the negative dependencies. However, for the hindcast models, the rotated 90 degrees Clayton copula is selected for the MIM season, which show an overestimation of SST chlorophyll-a coupling. And for the SON season, a rotated 180 degrees town copula type 2 is selected, which suggests an overestimated positive dependence. So for the perspective, as a next step, given the significant error observed in the output of chlorophyll-a models, future research should focus on developing alternative methods for predicting chlorophyll-a concentration, and it is also essential to explore how these relationships may change under climate change scenarios.